And both time period listed for the rights version. Yeah.
Okay, so this is sub-element 6 called circuit components. For 2 exam questions. There's only 2 groups. So this is a shorter section. And we're going to talk a little more detail about resistors, capacitors, inductors, get into solid state diodes and transistors, a little bit about vacuum tubes because they're still around, and they're neat, and batteries. And in the second group, analog and digital circuits, microwave ICs, display devices, connectors, and ferrite cores, or beads. So in resistors, but the only thing they care about on the exam is knowing about wire wound resistors, because they're actually made with a wire. It's actually an inductor with resistance wire. So they can cause a lot of problems if you try to use them at high frequency AC or RF because of the inductance, and it can be very unpredictable. They're normally used as power resistors in DC or low frequency AC circuits like power supplies and stuff. So why should we started without you?
That's fine.
You did this one. Wire wound resistor. Why shouldn't you use a wire wound resistor in an RF circuit?
It adds inductance.
Okay. Why is that bad?
Because it changes the resistance with frequency. I'm sorry, I just had to take a few minutes out to tell the wing chief of staff in a polite term to go screw himself.
Okay. Good on you.
He tried to make me the assistant wing operations officer. And I told him as soon as we get a new wing commander, I'll consider it. Under the current one, he's an idiot. I'm not going to deal with.
All right. Okay. So we don't want to use wire wound resistors in RF circuits. It can be unpredictable performance. Capacitors. The only thing they want you to know about capacitors, there's a lot, is that ceramic capacitors, which are probably the majority of ones that are used, because they're very low cost, very simple device to make. They're pretty stable. They come in the smaller values from a few picofarads up to you can get them into the microfarad range. And then we have electrolytics, which are used if you need a high capacitance, basically in a given volume. And these give you many microfarads. You can even get supercapacitors that are in farads that are relatively small.
And don't touch them until you've shorted them out. Because they'll hold a charge for a long time and kick your butt.
Especially in a tube transmitter with the electrolytics, and you're looking at several hundred volts.
Or in an old television set.
Or an old television. The electrolytics are polarity sensitive, and if you hook them up backwards, probably the best thing that can happen is they swell up and start working and leak. Worst thing is they can actually explode, and you get all kinds of paper stuff floating in the air. It's messy. We used to do that in the machine lab in college. Put them on 240 volts and throw the switch. They go off like firecrackers.
They were great for 4th of July.
Which of the following is characteristic of low voltage ceramic capacitors?
I think, oh, gosh.
Low cost, cheap. What are inductors? Coils of wire. Yeah, I guess they dropped the question about the electrolytics. Was in there until this cool. What are inductors? They're coils of wire that create a magnetic field, concentrated magnetic field, that stores electromagnetic energy, and we call that inductance, the ability to store energy as an electromagnetic field. We have air core, and we get very small values of inductance, typically used for very high frequency stuff where the other core materials won't operate at those frequencies. You used to see a lot of powdered iron core inductors used in radios, in the IF strips, and you could actually tune it by screwing the powdered iron core up and down inside the little transformer core. Today, we mostly use toroidal cores made out of ferrite material because you can get a large value of inductance depending on the material itself and how many windings you put on it.
And you were absolutely right about French. When I was saying 2 to 3 dB loss, that's usually that insulation principle, trying to tell power noise. In a antenna toroid, good one will only have about 2 dB insertions. So,
yeah, it will depend partly on how lossy the core material is. And one of the things we'll talk about in another chart is the difference in mixes and materials and how it affects the different frequency ranges and inductance values.
And make sure you use a plastic screwdriver if you're adjusting powdered iron core while it's under load.
Or just do it multiple times because you're offsetting. This way they make those fiberglass ones. So the core material can be optimized to operate at specific frequency ranges. And the other big thing is the magnetic field in the toroid is mostly contained within the toroid itself. You don't have very much magnetic field extending around it, so you can have them relatively close together without them interacting. Although typically, when they do put them close together, they'll do them at right angles. So there's even less effect. They can act as a capacitor. We talked about that before. If you operate it above its self-resonant frequency. So even though it's an inductor, there's what you call straight capacitance. What is the term capacitance called? Anyway, you can have capacitance between the terms themselves. So you will have a resonant point at some frequency because of the inductance, capacitance, reactances being equal. And if you operate above that, it tends to look like it's a capacitor instead of an inductor. That I don't totally understand, but I believe. So what happens when an inductor is operated above its self-resonant frequency? Oh, there you go. It becomes capacitive. Okay, I left this one in, but they took the question out. But you should know a little bit about rectifiers, particularly in power supplies. This is showing a simple single diode or rectifier power supply. So we're only conducting on half of the cycle. So we're getting a pulsating DC signal out that will then filter and kind of smooth that out to some DC voltage much lower than that.
Nicer if you have a bridge rectifier.
Right. You can either go with a full wave, which would be 2 rectifiers and the center tap transfer, or a bridge rectifier, which is a ring of 4 diodes. And those come today packaged in a single unit with all 4 diodes in it. So it makes it very easy to do. Back in the old days, we used to use selenium rectifiers. It's a stack of plates with selenium and some other material that acted as a diode and would handle a lot of power. I haven't seen one of those in eons. There were vacuum tube diodes. In fact, the very first one, the Fleming valve, British guy, was a diode. And he called it thermionic because you had to heat the cathode for it to conduct. But it only conducted current in one direction.
And before that, you had cat whiskers on a crystal.
And then in semiconductors, we have a p-n junction, which is a 2 pieces of semiconductor material that are doped or grown such that one has excess electrons and the other has a deficiency of electrons or an excess holes. And when you put those together at that interface, it acts like a diode and will only conduct current in one direction from the P to the N for conventional current, even though the electrons are going the other. So what is a solid state diode? There we go. It's a crystalline piece of semiconductor material, normally silicon, that is doped. So you get a P-type and an N-type, and this interface is what they call the depletion region, because you've got a bunch of holes on one side, a bunch of electrons on the other side. We represent that with this symbol, which shows the cathode as a straight line, and the arrow is the anode showing the direction of current. There used to be a question on the test about how you mark them. And normally, at least for smaller diodes, they would have a stripe on one end to indicate that's the cathode end of the diode. They dropped that question for some reason. There's basically 2 types. The ones you don't see as much are germanium diodes. They had a forward voltage drop of 0.3 volts. So in other words, you had to exceed 0.3 volts before it would conduct. It was the forward threshold voltage. If it's a silicon type, it's approximately 0.7 volts before it conducts. Now, there's other variations that have different voltages, but exam-wise, you only need to worry about germanium and silicon, 0.3 and 0.7. So what's the approximate forward threshold voltage of a germanium diode? 0.3 volts. What's the approximate forward threshold voltage of a silicon junction diode? Those are gimmies to get that. Transistors. It's another semiconductor device, normally made out of doped pieces of silicon. In this case, it has 3 terminals on it. and 3 pieces of material. And there's basically 2 types, there's bipolar and field effect. In a bipolar, we call the terminals the base, the emitter, and the collector. The base is the controlling element. In the field effect, we call the 3 terminals gate, drain, and source. And in that one, the gate is the controlling element. Now, the basic difference in a bipolar, it's a current controlled device. So a current on the base, between the base and the emitter, will control current flow between the collector and emitter. And the device has some gain or beta, so the current between collector and emitter is many times what the base to emitter current is. So that's how we can use it as an amplifier or a switch. In the case of a field effect, it works with an electric field that controls the current flow between the drain and the source. So the drain is equivalent to the collector and the source is equivalent to the emitter. Now, the reason they use different terms, I think, is field effect transistors came about from a practical standpoint a lot later. And people started using electron flow as opposed to conventional current flow. So that's why in the field effect, at the bottom, the one called source is the source of electrons. And the drain is the output or drain of the electrons. Even though you put a positive conventional voltage on it and you see conventional current going drain to source, that's really holes moving as opposed to electrons moving. But essentially the difference is bipolars are controlled by current on the control element. Field effect is controlled by a voltage on the control element. And you need to remember the names of base, collector, and emitter, and gate, source, and drain.
And field effect are more susceptible to EMP than others.
Well, that's why they put little diodes on your compensate for that. They are more sensitive. Basically, a field effect transistor works like a tube, like a vacuum tube, which is a voltage controlled current control.
Well, don't most modern receivers say limited something diode.
Yeah.
There you go. So this can have a lower threshold.
We normally are only using bipolars for power, but even now, most of the MOSFETs and power MOSFETs handle most of the powers. Even though they're still around, you kind of see them in general purpose stuff where it doesn't matter because you can get 2N 2222s dirt cheap. You get them off of Amazon, a pack of 100 for like $5. And they still work. So what is a bipolar junction transistor? Did I move on? Yeah. The little diagram down there kind of shows cross section of how one is actually made, and you can see the different layers. So you have a base emitter junction or on top, which is P material inserted in there, and it's going to control the current between the collector and emitter, which happens to be 2 N-type materials. So a very small microamp, typically current, is enough to control milliamps or more through the current emitter. Now, you can use it as an amplifier, or you can use it as a switch. Remember, it's got 3 terminals, base, emitter, collector. And we'll talk about amplifiers and switches. When we use it as an amplifier, we want to use it in this linear region. So you'll have in a typical circuit, which will have a little more complicated than this. This is the basic one. This is called the load resistance. And the slope of this line that's drawn here is the value of that resistance. So it's the ratio of the current to the voltage. Now, because of the gain of that transistor, for different values of base current, which is what these lines are showing, you see different values of collector. And where those cross that load line is the operating points. So if you use it as an amp, and at the one at the top we call saturation, where it's turned on fully, it appears to be essentially zero resistance. It's going to conduct maximum current. It's only limited by this resistor. The opposite end is we don't have enough base current to turn it on. So it looks like an open circuit. So we have no current flow. So as an amplifier, we want to operate somewhere in the middle of that, hopefully where it's linear operation. And normally you pick about the midpoint. So you would bias the current on the base to a point where it conducts enough current to be about the middle of this load line. If you're operating as a switch, okay, you're going to supply either enough current to saturate it or not enough current so it's in cover. So it's either on fully or it's off fully. So it has a minimum power dissipation when it's on totally because it has very low resistance. When you're operating as an amplifier and you're operating in this middle region, it's on all the time, so you're dissipating a lot more power. And that's what you find in a Class A amplifier, why they're very inefficient, because you're dissipating a lot of power. As far as the exam's concerned, you just need to know about amplifiers in the linear region and switches do at cutoff and saturation. What are the operating points for a bipolar transistor used as a switch? Okay. Saturation. So a field effect transistor is similar but different. It requires a voltage to create an electric field to control the current flow. And if you can see in the little diagram, there's a typical cross-section of a MOSFET, which has an insulating layer between the gate material. And that's where the electric field is between the gate and the base material over there. And that has a pinch effect and can control the current flow between the drain and the source. The main thing to remember is the gate for a MOSFET is separated by an insulating layer. That's the difference between the MOSFET and a regular FET, metallic, oxide, and it's this oxide or insulating layer where it gets its name.
They use the gallium arsenide.
For high frequency transistors, a lot of times they'll use gallium arsenide as the base material as opposed to silicon. And there's some other exotic ones, get into the microwave type stuff. Typically, your common bipolars or FETs or silicon. We do use stuff like boron and phosphorus to dope the material to make it a type P or an N type. Which of the following describes MOSFET construction?
No problem. Oh, no,
Don't second guess yourself.
I was not looking to see.
Yeah, read them all. Gate separated from the channel, which is the channel between the source and the drain, by a thin insulating layer of metallic oxide. Vacuum tubes. The British call them valves. We just call them tubes. It's a device that controls the current flow between elements that are in a high vacuum. When you apply a potential difference. The simplest one was the original Fleming valve, which was a diode back in 1904, where they heated up an element called the cathode and put a voltage on the anode and got electrons flow from the heated cathode to the anode. And it only flowed in one direction, so it was the first rectifier diode. Along came not very Armstrong? No. Anyway,
Fleming.
no, not Fleming.
Ian?
Huh?
Ian?
James Bond. Anyway, he added a control element, third element, which we call a control grid. And that allowed you to control the current flow between the cathode and the plate, anode. And you apply, it's like a field effect transistor. You apply a voltage to that control element, control the current. Now, one of the problems when they start trying to do higher frequencies with tubes is because these are plates, these are actually physical metal pieces in this tube. There's capacitance between the control element and the plate, which limited the how frequency range you could operate. So they came up with adding additional grids, which they call screen grids. In some cases, there's 3. And those allowed them, by applying different voltages, to reduce the amount of capacitance so they could operate at higher frequencies. So the purpose of those screen grids was to reduce the control grid to plate capacitance. And it's red because it's a test question.
So did they teach out what about 1 or 2? What?
I don't remember. I have played with tubes in decades. My last tube was built in a Tesla coil. Never did get it oscillate right. I have terrible time with oscillators. The typical reduction is like 8.025 picofarads. I think I left that in there because I think that pops up on the X-rays. Which element of a vacuum tube regulates the flow of electrons between cathode and Control grid.
The grid. There you go.
Grace.
And the heater, when it burns out, the tube goes out.
Now, they didn't used to always have separate heaters. Sometimes they'd actually heat the cathode. And then later on, they discovered it worked better if the filament heated the cathode indirectly. What's the primary purpose of a screen grid in a vacuum tube?
Alpha.
Alpha. Reduce the grid plate capacitance. And how does that work? Because you've got another plate in there
Series.
in series. It's going to have capacitance, but now we got what? 2 capacitors in series. It's less. Okay, batteries. Battery is a source of electrical power consisting of one or more electrochemical cells with external connections for powering electrical devices. A nice sort of legal sounding definition. We typically use them in amateur radio and handhelds. This is rechargeable batteries. If you're mobile, running off a car battery, which is a rechargeable lead acid battery, at least in most cars. I guess if it's a Tesla, it's not a lead acid.
I think they're still doing some sort of lithium. They're supposed to be rolling out a solid state something, but
If you're operating a base station, you may have backup power, it's battery backup. You might even have solar cells connected to that to keep it charged up. And if you're doing portable stuff like Byron down there at the end, you're using, what's your battery pack there?
12 amp hour lithium.
You want something lightweight so you can carry it around with a fairly high amp hour. How many is that?
12.
12. So common types of batteries are rechargeable and non-rechargeable. They still talk about nickel cadmium, although you don't see them that much. Their biggest thing was the very low internal resistance, so they could deliver very high discharge currents. With a lead acid storage battery, the thing you have to concern yourself with is the minimum discharge voltage. If you get down below 10.5 volts, not very good for the battery. But you tend to use lead acid batteries for very long life applications because they do last long. And then we have non-rechargeable, which is your typical carbon zinc flashlight battery, which I've tried, you cannot recharge them. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery?
See, Charlie.
Does anybody know what the nominal voltage is for a 12-volt battery?
12.65, I believe.
13.8.
No, it's flood voltage. Yeah.
That's why all that CAM stuff uses 13.8 volt.
And if you let it go below 10.5, make sure you've got a desulfating pulse charger.
Well, if you let it get down that low on your receivers, transmitters,
And I have salvaged more motorcycle and airplane batteries using a pulse charger. Huh?
Exactly.
No, the pulse charger puts a frequency on the direct current that is the resonating frequency of lead sulfide. So as it gets that pulsing frequency, it causes lead sulfide to shake loose from the plates in the battery and go back into solution.
Sometimes you can turn them upside down. What's the advantage of batteries with low internal resistance? Like just a NiCad.
Kind of toward
Okay, so we don't use wire wound resistors in RF circuits because they're inductive. Ceramic capacitors are cheap. Electrolytic capacitors have a high capacitance, but they're polarity sensitive. Inductors can appear capacitive above their resonant frequency. Toroids can give you a large value of inductance. They can be optimized for specific frequencies, and the magnetic field is mostly contained in the core. Rectifiers, they dropped from the exam, talked about it a little bit. They convert AC to DC. Solid state diodes, you need to remember germanium is 0.3 volts forward threshold and 0.7 volts for silicon. We've got two types of transistors, MOSFETs and bipolar. MOSFET is a gate separated from the channel with a thin insulating layer. That's the MOS, metallic oxide part of the name. And if you're using them as a switch, you're operating between cutoff and saturation. You're not operating in the linear region. It's either on or off. For vacuum tubes, the control grid in a triode regulates the electron flow between plate and cathode. I should say cathode and plate because it goes that direction. The tetrode, we added a screen grid to reduce the capacitance between the control grid and the plate. We have non-rechargeable and non-rechargeable batteries, nickel cadmium because they're low internal resistance and high discharge, and lead acids, the minimum discharge voltage that will affect the life of the battery if you go below. Okay. I'm just going to stop.